that. Yeah. Okay. Yeah, just one. Just one? Okay, thanks. Morning, everyone. This is Karthik Sundaresan from Cable Labs. I'm glad to be here. This is my first time at NANOG, and it seems like a great conference. It's very relaxed, great people. So today I want to talk to you about the upcoming DOCSIS 3.1 specification. We'll go through some of the key objectives. Oh, I guess my slides are getting cut on both sides. All right. We'll talk about some of the key objectives the MSOs set before we started the project. We'll look at some of the PHY layer and MAC layer design choices the team made for DOCSIS 3.1 and why we made those. And then we'll look at how a cable operator could evolve their network architecture from DOCSIS 3.0 to 3.1. So for those not familiar with DOCSIS, DOCSIS is a global standard. It's deployed across Europe, across North America, South America. There are more than 180 million units, CPE units shipped. The architecture is mainly, DOCSIS is focused on the access network, right? The cable operator has video services, has IP high-speed data services, has voice over IP telephony services. All of those are in the core network. They get transported to the regional head ends, which is where you have your CMTSs sitting. And DOCSIS is the protocol between the CMTSs and the modems, right? You have a hybrid fiber coax plant, so you have fiber going as close as you can to the customer, to a subdivision or to a building or whatnot, and from there the fiber gets split up as coax. And usually you have about 500 homes passed per node, per fiber node, and as time goes on, MSOs are pushing fiber deeper and deeper, so the number of customers per node is decreasing. So, and just a quick slide on history. DOCSIS started back around in 1996 with DOCSIS 1.0, with providing just basic high-speed internet access. There have been new versions of DOCSIS every few years, 3 to 5 years mainly. DOCSIS 1.1 introduced support for quality of service, and then you could enable voice services, gaming, streaming. DOCSIS 2.0 provided capabilities for both upstream and downstream symmetric services. 3.0 took that to the next level with channel bonding, bonding multiple channels together, and also added support for IPv6, which took some time for vendors to implement, but I think DOCSIS 3.0 cable modems now have, and CMTSs support IPv6 naturally. Like I live in Denver and I have native v6 service in my house. And 3.1 is really a big change. We're going to really wideband channels. The 6 megahertz channels are left behind, and there's a new PHY layer choice, which is OFDM, and we'll talk about that in a minute. So the key objectives for DOCSIS, which the cable operators decided together, were the following, right? The most obvious one is higher capacity. We want to be able to deploy at least a 10 gigabit per second downstream, at least 2 gigabits per second on the upstream, and we want to do that at a decent cost, right? We want to reduce the number of the dollars you pay per bit to get it to the customer. Plant adaptation, that talks about different MSOs have different cable plants, different conditions. Some are cleaner, some are not so much, and you want to be able to adapt your technology to work on each of those plants. Migration strategy, that's more about deploying the new 3.1 bandwidth and services as and when you need them, right? And the last is you don't want to dig up the whole cable plant and relay fiber and coax, you want to operate on what you currently have. So I'll go through each of the goals, and I'll walk through some of the choices the 3.1 technical team has made so far. So the first goal for higher capacity, how do we enable that? The first one is a new FEC. The previous versions of DOCSIS were using Reed-Solomon. I think finally the technology and the implementations have caught up where LDPC is becoming more easy to implement. So low density parity check, FEC is a choice for DOCSIS 3.1. What that lets you do is on cleaner plants, it lets you go to higher modulation orders. So DOCSIS was currently 256 QAM or 64 QAM in the downstream, but now we're talking of 1024, 4096 as mandatory requirements, and modems and CMTSs could optionally support all the way 8K to 16K QAM as well. So giddy numbers in terms of QAM. And just as an example, just going from 256 QAM to 4096 QAM, 8 bits to 12 bits will get you about 50% more bits per second per hertz. So FEC is one, and the other point for higher capacity is more spectrum, right? There's no getting away from Shannon's law and Shannon's limit. If you want to deploy higher bandwidth, you need higher speeds, you need more bandwidth, right? No doubt about that. So just as an example, with DOCSIS 3.1, 500 megahertz of downstream spectrum is good enough, and if you're doing 10 bits per symbol, then that amounts to 5 gigabits per second, right? To do the same in DOCSIS 3.0 would take us about 780 megahertz. So we're just getting leaner and packing more bits into the spectrum available. So the next goal of cost reduction and plant adaptation. Here, the biggest choice is OFDM, right? Folks are already familiar with OFDM for 802.11. Many other wireless technologies already use OFDM. It's more robust. It's more efficient. The idea is you take a bigger channel, a big chunk of bandwidth, and you split it up into smaller subcarriers, and each of the subcarriers are orthogonal to each other, so that minimizes interference. And again, the goal is to transmit more through the bandwidth you have. So moving to OFDM means you're moving away from the legacy DOCSIS or the legacy video 6 megahertz in the US, 8 megahertz in Europe channels, and now the DOCSIS data channels are going to be much bigger. So it's all the way from 24 megahertz to 192 megahertz, right? So big chunks of spectrum. And in terms of plant adaptation, now that each of these big chunks of 24 or 96 or 192 megahertz are split into individual carriers, each carrier is either 25 kilohertz or 50 kilohertz wide. And so that means you can, depending on the noise on the plant, if you have noise in certain areas, then you can use a lower modulation on those subcarriers. And if other parts of the plant are cleaner, then you can use higher modulation. And essentially you can, depending on plant conditions and as they change, you can change the modulation orders on each of the subcarriers and get a greater overall throughput. Migration strategy. Here, the DOCSIS 3.1 modems will of course operate on 3.1 CMTSs, but they'll also operate on 3.0 CMTSs. So it's one iteration of backwards compatibility. So that way, the way I would see it is, modems new modems are manufactured first. They get deployed onto existing CMTSs or CCAP platforms, and then over time, as operators make their investments on the CMTS side, then they can actually slowly turn on the new OFDM PHY and the new 3.1 features. And 3.1 CMTS also will support the existing 2.0 and 3.0 CMs out in the plant, so there's no need to go rip those all out right away either. The other key decision the team made was to support channel bonding. And the idea is even a 3.1 modem will support 3.0 style channel bonding, 24 downstreams, 24 channels on the downstream and 8 channels on the upstream. So just off the gate, a 3.1 modem would be equivalent to a 3.0 modem and will support OFDM channels as well. So equivalent and better. And lastly, you will be supporting bonding across OFDM and SEQUAM channels. And the last objective was existing network operation. Here, at the graphic at the bottom, you can see in the cable plant, all the upstreams are below the downstreams. And we're sticking with that. The main thing we're doing is moving the split where the upstream stops and where the downstream starts. So today it's from 5 to 42 or 45 megahertz, and in Europe it's 65. But it's going to go up to 85. That's the mid-split option, and then there's a high-split option of 200 megahertz. So even on the upstream, you'd have 5 to 200 megahertz, which is opening up a whole new bandwidth for upstream, right? Somebody was talking to me, hey, I get 50 by 5 or I get 100 by 5. When am I going to start getting more upstream bandwidth on a cable plant? And this is kind of the answer to that. Now that there will be more bandwidth allocated to the upstream, as MSOs open up that bandwidth, the service speeds will also increase. On the downstream, it starts at 252 megahertz and goes all the way up to 1.2 gigahertz. There would need to be some upgrades to the plant if you want to go to 1.7 gigahertz on the downstream. But that, in any case, that's an option, and the vendors will be implementing it. So over time, if you want to turn on, if the operator wants to turn on those features, then you have that capability. Okay, so in terms of, we looked at some of the choices already. We talked about the higher orders of modulation. We talked about OFDM. The graphic on the far, on the left is a new convergence layer we talked about. So the team has been working at DOCSIS 3.1 for about a year and 2 months now. It's got more than about 100 or so contributing engineers from all the vendor companies. And there have been a lot of analysis and discussion and trying to figure out what are the exact parameters we want to choose for the new DOCSIS 3.1 specification. So there's been decisions made on what are the channel bandwidths we'll support, how many subcarriers would be in each of those, what are the varied FFT sizes, what are the frequency ranges, where are the splits going to be, what are the modulation orders supported, what kind of FEC we would support, is it something, so for DOCSIS 3.1 the FEC is, looks very similar to the DVB2 FEC on the downstream, and on the upstream it's a new LDPC FEC. Fidelity requirements, proactive network maintenance requirements, which started in DOCSIS 3.0. A lot of those requirements are making its way into DOCSIS 3.1 as well. And then the new convergence layer, right? Up till DOCSIS 3.0, the DOCSIS downstream video channel was essentially an MPEG channel. It looked like a video channel. It had its own PID. And you just tuned to that downstream and then decoded, the downstream data was encapsulated within that MPEG. For 3.1, we're kind of getting rid of that, obviously, because we're getting rid of the 6 megahertz channels, and now it's the new convergence layer is just you encode your code words as FEC code words, and you just ship them down the wire. Channel bonding, we talked about it a little bit already. OFDM channels are treated just like single carrier comm channels. We'll look at some graphics later, and it'll make more sense, where 3.1 essentially says we'll support bonding between OFDM channels, bonding between single carrier QAM channels, and bonding between OFDM and single carrier QAM channels, right? So bonding between everything. So at the PHY layer, these channels are different, but at the MAC layer, you stripe the packets across either your single carrier QAM or OFDM channels. And the other decision the team made is to allow for, along with bonding, there's also support for time and frequency division multiplexing. So you could have your existing single carrier QAMs on certain frequencies, and you want to turn on your OFDM channels, perhaps at the same frequencies. You could just TDM them, right? Or you could separate them onto different frequencies, and that's the way you start your deployment. On the MAC side, so 3.1 is mainly a new PHY, right? It's a new OFDM PHY, and MAC essentially has updates to support everything which the new PHY has, right? So it's a new OFDM. How do you range on that? How do you figure out, you know, the downstream channel parameters? How do you figure out the upstream channel parameters? The MAC has changes to support the new PHY. So, you know, ranging, probing, profile is a new concept in DOCSIS 3.1. You can think of profile as the modulation orders for a set of subcarriers. And, you know, on a certain subcarrier, you could do 256 QAM, or if it's really clean, you could go up to 1024 QAM or 4096. And how do you figure that out on the fly in the plant? And the idea is the CMTS would send down a command to the modem and ask him to send up test code words on some of the new profiles, and the modems would well, on the downstream, the CMTS would be sending down the test code words, and the modems will report back metrics saying, hey, I could decode so many code words, and I could, you know, these were the number of bit error, this is my bit error rate, this is my MER, and report that back to the CMTS, and then the CMTS can make a decision saying, hey, these channels or these modems I can put on these profiles, and either at a higher profile or a lower profile, and so that they have the right throughput which they're capable of. DOCSIS 3.1 allows now 2,000 byte PDUs. I think the previous versions of DOCSIS supported 1,500 byte max MTU. So this is mainly for business services and L2 VPN and the other type of services which need more headers on top of the 1,500 byte payload. There is new energy management technologies defined, light sleep mode. If the modem is not transmitting data, it's going to go to sleep, and you can wake it up at some time when it needs to transmit data. There are new timing requirements. There's a DOCSIS time protocol, which is going to allow the modem to be very tightly synchronized to the time on the CMTS. And what that enables is the modem to now maybe be a 1588 clock on the customer side. So again, for business services, that'll be a big win for that. The next topic is active queue management. I think somebody at the trace route track talked about buffer bloat. This directly addresses some of those problems, and active queue management algorithms are being defined on the modem and the CMTS. And hierarchical QoS is a, you know, more bandwidth management, not at a per customer level, but more on a broader traffic class level for an MSO to manage video traffic versus voice traffic as a whole. And you know, all the other concepts from DOCSIS 3.0 and previous versions of DOCSIS, concept of service flows and classifiers and all the quality of service and everything carries over, right? None of those are taken away. These are just some of the new things I'm talking about. And again, this is at the 30,000 feet level. I'm not getting into too much details for the amount of time we have. So in terms of migration to 3.1, today, starting from the left, we have mostly 2.0 modems in the plant and 3.0 modems in the plant. There are a few straggling 1.1, 1.0 modems, and hopefully they're out of here soon. And MSOs are deploying, any new deployments is all DOCSIS 3.0, right? So we envision the first thing which would happen is DOCSIS 3.1 CPE cable modems will show up first, and they get deployed on it, and they're just working on existing DOCSIS 3.0 CMTSs. And then over time, as more 3.1 equipment makes its way into the plant and MSOs free up the spectrum for OFDM channels and make the investment for buying 3.1 CCAP and CMTS equipment, then they get into the plant as well, and you can start turning on some of those OFDM features. And then over time, you would expect the 2.0 and 1.1 to be completely gone. You'll have more of 3.1 CMs, and you kind of stop deploying 3.0 CMs at some point of time. And then the last step would be to increase the spectrum, right? From 5 to 45, maybe you go to 5 to 200 for the upstream, and for the downstream, you go from 200 to 800 or 865 where it's today to 1.2 to 1.7 maybe. All right, so this is a graphic of how the cable plant looks today. The dark blue on the left is the outer band and the upstream. The light blue on the left is the upstream, the DOCSIS, legacy DOCSIS channels. The analog TV channels, hopefully they're all gone in most of the cable plants, but many still have it. And then after that, you have the legacy outer band downstream. This is the outer band. When I say outer band, it's for set-top boxes. And then somewhere in the middle, in the high hundreds, you have 8 or 16 channels devoted to DOCSIS data channels. And over time, we're going to see more DOCSIS 3.0 channels being turned on. That's the tomorrow graphic at the bottom. And these channels are being, there's channel bonding across all of these channels as well. And the idea would be, over time, the orange channels are the new OFDM channels. You start introducing them either in overlapping bandwidth, and you do some kind of FDM or TDM for those, and you bond across the legacy DOCSIS 3.0 channels and the OFDM DOCSIS 3.1 channels. And then in the really long term, either you turn off some of the DOCSIS channels and just do OFDM, or you have a mix of both, and you're just bonding across those. And you also change the split from 45 to, say, 85 or 200 megahertz. Okay, so what does this mean for the DOCSIS 3.1 network? It's more bandwidth means more spectrum, right? And where do I get the spectrum? Today the cable operator has video channels going over those. So what that automatically means is many MSOs will have to turn off their video channels, and those video channels will be going over IP. They'll be going over DOCSIS 3.1, right? I think many MSOs are already thinking along those lines. Start small with a certain block of OFDM channels and start growing incrementally over time. And you can optimize for certain parts of the network where you know you have high bandwidth customers, then that's where you'd start your deployments initially. And as you clean up the plant, clean up the coax, that's when you'd see more benefits for efficiency and operational expenses. So, and any investments back in the core would also help all the new bandwidth which is coming up through the access network. So to summarize, and my main takeaways from this would be for 3.1, we have a new LDPC FEC, we have the new OFDM upstream and downstream PHY layer, and the MAC layer changes to support everything in this new PHY. And then you have backwards compatibility in terms of features and config files, and also things like channel bonding, where you can bond across QAM channels and OFDM channels. The upstream stays below the downstream. There's no top split. There's no upstream on the other side of the downstream. And then you're starting to work on the existing plant without too many changes. So the cable industry is working hard to enable faster speeds and faster services. The goal is to get there cost effectively and to provide multi-gigabit services. That's really the goal. I expect multiple generations of 3.1 silicon and software to come out there, and they'll start off at lower gigabits per second, working all the way up to 10 or so gigabits per second. And there are options for new spectrum. You can turn that spectrum on as you need it, and it basically tries to squeeze out more bandwidth from the existing cable plant, right? That's the more expensive part of relaying fiber and cable. We're trying to squeeze out as much bits as we can out of that. So that's all I had. I'll take questions.
Only one. Anti-Capella 5 nines. Excellent work you guys have done on a pretty bold spec. I'm curious about one thing, or at least one thing, but I'll keep it just to one here. Automatic repeat requests are features of a lot of complicated, and today obviously very fast PHYs and MACs. Witness LTE. I mean, despite having ridiculous scalability and moving hundreds of megabits over really crappy air links, they still found gates and power left over to do sequencing and retransmissions. I'm curious if that's been part of your research work, part of the information behind this decision, and if it is behind it, I'm curious why it's absent.
So can you say, you said automatic?
ARQ.
ARQs, okay. Yeah. So DOCSIS is, so we did think about that some. DOCSIS is mainly a shared medium on the upstream, and so I don't think the request mechanism has changed from what it was before. Multiple cable modems can make requests for bandwidths, and if you collide, then you would retry at a later point. But then there are these station maintenance periods where you allow the modem to request, so they just back off, and if their request doesn't get through, then they back off and send a request at the next chance.
I'm referring specifically to user traffic, like a PDU you've already sent to the wire was damaged beyond repair. LDPC couldn't decode it. Of course, there's long-ranging adaptation in 3.0 and 3.1, as you rightly pointed out, which is excellent. And it seems like it's been extended to a very high-resolution manner through the OFDM resource blocks and everything else.
Right.
But if I lost enough and I couldn't decode it, the chance to retransmit it is on the physical layer sub-millisecond,
right.
Tens of microseconds maybe.
Right.
If I have to have TCP do that or UDP do that, that still is unfortunate. So I'm curious because I see very complicated PHY and MAC systems, LTE and HSPA plus and so forth,
right.
continuing to provide some sort of user level and higher retransmission scheme. in the Mac.
Right.
So it has to. It seems to me, intuitively anyway, that there's enough gates to do it. So people are doing it, we're sequencing it, and we're retransmitting it. That's pretty effective.
Right.
As a strategy, of course, to maybe cheapen the forward error correction. For example, if I could get 2 nines likelihood out of
Right.
FEC and fix that last 1% through retransmissions periodically, that might be better efficiency, right?
Right.
So I'm just curious why that, or where that isn't here.
Right. You're right. So that there is no automatic retransmission at the PHY and the Mac today. And let's see, I think DOCSIS traditionally has been just a layer 2 bridge, right? I mean, there is some layer 3 awareness where in terms of classification and things like that. But the design team never went, I think the complexities of holding onto a packet and sending it and trying to see if it got to the other side, getting a response back, we're not doing that.
Sure, thank you.
Okay, sure.
Great, thanks very much.
All right, thanks.